should we ask Ivette and Chris just maybe open up the discussion a little bit from what you, if you have any questions or responses, and of course then we can do the other way around as well, because you are this morning's speaker. So why don't I'll give it first to Ivette.
Okay, so yeah, I'm a bit new to this, so philosophically, I think that it's the right way to start. I think that we've been doing physics for a very long time in the reductionist way, taking little pieces, atoms and so on, and putting it together. And then we sort of break the universe in little parts, and then we want to put the little parts together to unify the whole universe. And it's not surprising that that doesn't work. So from a philosophical point of view, I think that there's one universe, because I'm not a many worlds person, and I think the universe is already unified, and it's us that we're limited in our theories, our instruments, our intelligence, in all these ways that we see the universe in little pieces. And of course, I mean, the reductionist approach has worked super well for a very long time, and it will continue to work. We will, when we have lasers and technologies, and so thanks to the way we do science. But I think maybe to approach other questions, we need, I think, to recognize that the universe is a whole, and that it's all interconnected, and that maybe starting with approaches like yours might be very beneficial. I was telling him that I live in two worlds. One is like my philosophical standing. Actually, like now I've done a lot of things with the hat, and I put my hat on when I'm talking, because from the physical point, when I work in the usual reductionist point of view. So I guess, like, for me, thinking about, but the thing is that he's going to talk about quantum mechanics tomorrow. So I don't know what to ask. Yeah, okay, so what I want to ask him, no, because as I said from my talk, I've been following up on Roger's idea that there is a collapse of the wave function. But a very big problem, and this I'm going to get this criticism when I finish my work, is that people that work in relativity, they will say, okay, collapse is a problem because, well, if you're just thinking about the standard thing where time is absolute, is not a problem because all observers would agree that the state collapsed. But now if you go to relativity, then you get a problem because it's funny, like in one branch it collapsed and not yet in the other branch, and so on. So that's why I think that you have to modify relativity as well in the ground theory, and then to be able to get something consistent. But I am curious, like, if your perspective or theories could help address questions like that.
Yeah, that is a very interesting question, because as we are going to show you tomorrow, when we apply the mass wave concept, which we get after we have cleaned Planck constant from the hidden C inside Planck constant, then we have that we can write Planck equation is more H0, which is what I call the intrinsic Planck constant divided by C. So intrinsic Planck constant divided by wavelength is kilograms times C to the second. Then the Planck equation gets exactly the same form as the rest energy for mass m. And from that we can further continue that, which means that we can then describe a particle as a Compton wave resonator. And when we put a Compton wave resonator in the motion, then we can observe the Doppler effect in the front wave inside the resonator and the back wave. And the sum of these two Doppler shifted waves is exactly the wave carrying the momentum of the object. And it's exactly carries exactly the same momentum as what de Broglie wave describes. And with this concept, once a particle is moving, let's say, through a double slit system, the resonator itself takes one of the, just like in Bohr's idea, it has the trajectory, and it's followed by a wavefront which carries the momentum. And when the particle hits the screen, then the velocity is stopped, which means that automatically the momentum wave disappears. So there's no magic in collapse.
You don't have a collapse.
No, it disappears naturally.
Mm-hmm.
There's no momentum if we stop the motion. Mm-hmm. Very simple.
Yes, we'll
Yes.
have to test it in the experiment.
Yeah, I'm afraid all my questions are to do with quantum mechanics as well, although I have to say that the experimental results that you presented are, to me, a non-specialist in the field, quite convincing. I mean, you showed that your theory matches the predictions where the other theories fall down. So I think, that's a big plus. Plus, it's got a preferred frame, so I really like that idea. It solves a lot of problems. But what I see missing, and perhaps this is a question for tomorrow, is a partial differential equation for your waves. A differential equation for your mass waves. So we don't know how they evolve in time, because we have no equation for that, unless I've missed that somehow.
I'm not sure that I understood the question before. But when I checked from my moving Compton wave resonator, I got the momentum wave. And when I check the wave number of that wave, it's exactly the same as what we have in Schrödinger equation. So that it proposes that maybe the Schrödinger we probably make it a physical explanation to the wave function.
Okay.
Maybe.
So your differential equation for how this wave propagates would be the Schrödinger equation.
In its simplest form, let's say. So that's an area where I have not went deeper in. So that with it, maybe Petri can go a little bit further.
Yes, hello everyone. My name is. I can introduce myself also. My name is Petri Lievonen, and I got made some presentations already at the UCL workshop in London, where I talked about Dirac equation and some Clifford algebras and that kind of stuff. I've been helping Tuomo now maybe for 2 years part-time, and it's really vast work. And I'm always interested in new ideas, but also I'm aware that things are not complete, to say the least. But they are really interesting, like geometric, because Tuomo has this engineering background, and visual thinking is so important, and simplicity and clarity is so important. So there are really nice, like geometric ideas in there that could have some pedagogical like usage in the future in some phenomena. But of course there are you can't take du now and somehow calculate all kinds of various experiments. There are vast amounts of experiments that Tuomo has analyzed, but not like complete. And also I'm really aware of like the relativity principle and how it's handled in DU. There's this even and odd distinction, and Tuomo mostly talks about the even side because his mathematics is scalar mostly. And when you take also the momentum into account, you have this movement and things become much more difficult. And also in terms of gravitational expansion of the systems, there's so much empirical evidence and empirical problems, I can say, how you interpret those data, because the astronomical unit is defined as constant, and how does it actually come into the simulations. But otherwise, I'm really happy to help Tuomo here, because this is a free country and free science, and it's not too much, resource use if few people study these kind of issues too, because we need new ideas, but we have to be creative, but also and curious, but also a bit hesitant into the next steps.
Okay, thank you, Petri. Also, may I add that no doubt we are in safe, so that the reality is not dependent the way we describe it. It is what it is, and we success in describing it better and more or less understandable. But the reality is what it is. Do you agree with this?
It is what it is. Yes. I wanted to ask you about gravitational waves, because that's something that is being tested all the time.
Yeah, that's also a subject. I succeeded in deriving the Taylor formula for the decay of pulsar systems. I derived that from the rotation of orbital angular momentum in the fourth dimension. In the dimension, and it gives essentially the same result as the Taylor equation, which is derived from quadruple momentum, quadruple gravitation. And the only difference is that from that derivation we get the result that circular orbits do not radiate, but with Taylor's equation also circular orbits radiate. And basically in dynamic universe framework there's quadruple momentum as well, so that it's not question of the model or the framework, but the aspect we are using for the calculation. But in my terms, gravitational waves for me looks more like should be called rather the mass waves as well. So,
sorry, I give it just a really quick one. Yes, just one sec, because that's you're talking about the source. But then, like LIGO, for example, I would suppose that you have the mirrors, and that the universe itself would be pushing the mirrors, right? So one thing is the source, and the other thing is like the measurement of the effect. So how do you see that?
What kind of measurement you mean?
So in LIGO you have the big mirrors.
Yes.
But I would suppose that your theory must predict that those mirrors are affected by the big universe in a way, right? So how do you factor that in together with the gravitational wave, or how do you look at that experiment?
You are looking the way the gravitational waves are detected. So that I think that basically the same effects are in dynamic universe framework. So that maybe we call the quantities differently, maybe, but basically the phenomena must be the same. I can't answer more accurately.
Yes, I had another question which actually just occurred to me with this solar system expanding. Does everything expand? Are we expanding in the same way?
Atoms do not expand.
Because
they are, let's say, they are not gravitationally. Atoms are not gravitationally bound. That's the difference, And that mathematics shows it very clearly that the Bohr radius is not expanding. That's very essential. Otherwise, if they did, we didn't notice redshift at all, because everything was scaling the same way.
Yeah.
Let's have
No, you shall
Peter.
say-
Yes, we can have questions also from the.
So the Bohr radius doesn't expand. So I assume h bar changes. H bar, h balance constant. I mean, if C changes and other things don't change, what are we supposed to see? That's going to be difficult.
It takes some time to go through all the equations where we have the Planck equation, Planck constant, because we need to remove C systematically from everywhere. But the result is that the fine structure constant turns out to be a pure geometrical or numerical factor. And that was very interesting result from cleaning the Planck equation. And when we can, I will show that tomorrow, so that we can see how the Planck constant is built from the electric charge, vacuum permeability, and the velocity of light. And those are the electrical vacuum, electron charge, unit charge looks like being constant. Mu naught, which is the vacuum permeability, is constant. Velocity of light changes with the expansion. And then the intrinsic Planck constant is independent of the expansion.
Yeah, but nothing, what else could be then dependent on this expansion apart from the velocity of light?
I guess I could tomorrow show a table that is like a current proposal of how the SE units should vary together to be somewhat consistent. And the way I translate Tuomo's work is that his C is the coordinate C in general relativity or in Schwarzschild space. And instead of using a constant local C, he wants to make the formulas in such a way that you can use the gravitationally time-dilated C in the formulas. And it results directly, at least the scalar part, results directly into correct physics. And I can show you, because then the fine structure constant has to be constant for electromagnetism to be like consistent. And from there you can deduce stuff, and then from the magnetic permeability and electric permittivity you can make all those like somewhat work. But also they are really, Boltzmann constant needs to have C squared. Yes.
I'm a bit astonished that only the C changes. And
No. There are a lot of, which need to change in sync, so that it explains the observations that we see now. Yeah. Because we can measure the gravitational time dilation in millimeter scale. But that is it might give something new, because usually that is delegated to the metric. You just calculate as if you are calculated locally using SC second and stuff. But actually when the gravitational time dilated C changes, then all the other stuff needs to change from the coordinate times perspective. And that might, but it's so much easier to do it on scalar, on the even part only. But then when you have movement and odd part, then it's more difficult. But there might be something really nice ideas there. Yeah.
Thanks. I just wanted to ask a specific special relativity question. And then it does kind of link to something that Ivette was saying about when you have relativistic quantum mechanics or quantum field theory, you don't exactly have particles. But that in a second. If I'm thinking about Alice and Bob, and Alice is standing in place, and there's a flash that goes off 100 meters in front of her. All right, there's a flash that goes off 100 meters in front of her, And Bob is, when the flash goes off, Bob is standing in the same place as her, but he's going faster than her towards the flash, right? So standard special relativity, we would say that you've got a accelerated frame of reference, and so the flash would happen at a different time for Bob than for Alice. And in your presentation, you had you showed how you could get you could have something. I drew it down as I wrote it down as in the forward light cone. You had this formula where you had a straight line going to the right, and then a diagonal line, and a straight vector going to the right, and then a diagonal vector that was this extra addition term. Do you know the one that I'm referring to? So that was how you got the usual prediction of special relativity for things in the forward light cone. Does this ring a bell? Well, you know what I mean, Petri. Yeah, it was on the same slide as the complex momentum part. Well, my question was, I did understand that you got the standard prediction for things in the forward light cone, but for things outside of the forward light cone, standard special relativity would say that from Bob's point of view, those happen in the those happen after Alice thinks they happen. And I just wondered how, so you've got this diagonal arrow that gets you the correction for the forward light cone, but I don't see how that could work for things outside of the forward light cone. That was what I was thinking about.
Yeah, I can personally imagine that there are all kinds of problems, especially in that kind of like kinematic situations, which have like common thought experiments that have been described in books. But I can tomorrow perhaps show, if the time allows in my presentation, one way to conceptualize this Tuomo's energy momentum relation in terms of Kudermannian function, because with Kudermannian function, you can map from hyperbolic space to elliptic space or circular space. Yes. So then using exponential function, you can show the equivalence, at least on the static setting. You can show the equivalence between the hyperbolic energy momentum relations and this Tuomo's relation. But there's a big problem because usually the rapidity is then the exponential, like the exponent. But Tuomo doesn't use that. So I think there are problems in terms of velocity addition formulas. But Tuomo's main point is that we should always try to think in terms of energy and momentum and where the energy is got from. Because actually we can't now, accelerate from here kinematically, however we want. We need to get the energy from somewhere. And that is, every time when you design an experiment or you think about the experiment, you should think about that, because it links the observer and the observer together. We are some way through the history where the energy is from.
Okay, now I think we must, we have a coffee break, and you see, it's a little bit tight because then we have the next talk and we have to be out of the building also by 6. So I suggest that we now thank our panel, go for coffee, back here at 4 o'clock sharp to listen to Henry.